Good afternoon and welcome to the Energy Seminar for 2018 winter quarter. This is our first seminar for this quarter. It's my great honor and pleasure to introduce Austin Sendek, who's actually one of these really phenomenal special PhD students we have here at Stanford. As the faculty could tell you, and after a few drinks, they're the ones that do all the work here, right? All right. So Austin is going to talk about building a better battery with machine learning. So we get kind of another cut on interdisciplinary research in a big way. So most of his research, as he'll describe, is essentially using big data techniques, machine learning, to more optimally design search strategies through different materials configuration than what one might do by just kind of random choice, I guess is the way he puts it. And he's been working in the lab, as you can see here, with Yishui and Evan Reed. He's in applied physics, but personal note, I first came across Austin when he was doing one of his other kind of non-day jobs. He was the very successful, in my view, vice president and then co-president of the Stanford Energy Club. And I think it was during those years from 2015 to 2016 or 17 where I was lucky enough to be on his advisory board that the Energy Seminar got built up to be as big and formidable as it is today. His work has been popularized through many media outlets, including, as you can see from his bio, ABC News, Science Direct, Scientific Computing, and so on. So with that introduction, I think your work was also mentioned by William Chu last quarter as well, if I'm not sure, either here or at the GSEP workshop. So it's quite a hot topic, you might say. So Austin, take it away.
All right. Well, thank you, John, for the introduction. Am I on now? Yes, maybe not. Hello? Can you hear me? I can just yell if I need to. We good? All right. I'm getting the thumbs up, so I'll just go ahead and go. All right, well, yeah, thank you for the introduction, and it's really an honor to be here at the Energy Seminar. I'm a fifth-year PhD student, as John mentioned, so I have about 6 more years to go before I'm out of here. And one of my first, actually the first thing I did at Stanford was I participated in Precourt's summer program, the Energy at Stanford and SLAC program. And that really set me up, I mean, really well to spend, these next 4 or 5 years really kind of, ingrained in the Stanford energy community. And it's been a pleasure to work with Arun and everyone else at Precourt over the years. And it is great to be here. So the formal title of my talk is Building a Better Battery with Machine Learning. I think the reason I got the invite to speak here was because I spoke at GSEP, and I called it the Wild West of Material Science and put a cowboy hat on and seemed to get a big laugh. I don't have the cowboy hat here, unfortunately, but that's sort of another way of thinking about this. We're sort of venturing into this unknown part of material science where we are combining what we know from the sort of conventional approaches with these new ideas from big data and machine learning to accelerate what we're working on. And I'm also a big believer in starting presentations with a joke. So I just found this one on Twitter yesterday, and I thought it was hilarious. I don't know if you guys think it's very funny, but so Robin says the Batmobile won't start. Batman says, check the battery. And Robin says, what's a Terry? Because Batman puts bat in front of everything. Okay, anyway, all right. Okay, tough crowd. John did call me a very stable genius before this talk, so I'm not completely crazy. Okay, so let's get going here. So I don't think I have to really convince this crowd of the importance of energy storage. I'm sure we're all aware of how important it's been, and lithium-ion batteries in particular have enabled major innovation across the spectrum of energy technologies. Of course, we all know about automotive with Tesla and other electric vehicles. Putting renewables on the grid, batteries have been used for load balancing. There's been some recent deployments down in Southern California for this. Now even there are companies thinking about heavy equipment being powered by batteries like airplanes. And of course, mobile electronics. So they kind of run the gamut of powering all kinds of technologies, but we can't get around the fact that these batteries aren't perfect. There are sort of, I think, 4 main areas where technology can get a lot better. Safety, of course, should be the top priority. Safety in batteries needs to be unquestioned, and I think it's very questioned right now. So that's something that needs to be improved. Energy density always needs to come up. Cost always needs to come down, and cycle life needs to improve. So especially if you start thinking about electric vehicles where you want to be able to drive for 10 or 20 years without replacing the battery, or you want to put batteries on the grid and you need to cycle them in little pieces here and there for 20 years, whatever it might be. We need to have really excellent cycle life from these devices. And so when we think about ways that we can improve these metrics, one of the aspects of battery technology that is kind of at the heart of a lot of these problems are the electrolytes. So this is a schematic of our battery. We have an anode and a cathode. Those are your two terminals. And then you have this electrolyte in the middle that separates the two. And it mediates the transport of lithium back and forth as you charge and discharge the battery. And so in commercialized cells, and the cells in your phone, in your laptop, these are organic solvents. So they're liquids. We can't use aqueous or water-based solvents because lithium reacts with water. So we have to use these. And they work well by most accounts. The lithium flows through them pretty quickly. They're manufactured at scale. But organic solvents are a problem. Other organic solvents you might know of are like gasoline, nail polish remover. They're very flammable. So if you were to overheat the battery or puncture it or catch it on fire, that's going to be a huge issue. But aside from that, they're also not great because they're very reactive. So you can't put a large voltage across a liquid electrolyte because it'll start to vaporize, it'll start to react, break down. They are also low density, so you can't make really small devices, and they don't suppress dendrites. And dendrite growth is one of the main causes of early battery death. So these don't really do much for that problem. So what we want to do in our research is we want to replace that liquid with a solid material that can do the same job, that hopefully has all the benefits of the liquids without these major drawbacks. So solids are just sort of inherently more stable and less reactive. They're higher density, so you can potentially make smaller devices. And they're very rigid, so they can suppress this growth of dendrites and potentially lead to increased of cycle life. So solids can really help us on all four of these metrics that we originally discussed. So this is all really to convince you that solid electrolytes are a really fascinating and I think very promising way to go to improve on battery technology. And so the question that the people often ask is, well, okay, if this is so great, then why doesn't it work? Why aren't we doing this now? And the short answer is that we've been trying to do this for a long time, and we haven't really been very successful. So I think nothing really illustrates that better than the juxtaposition of these two papers. This is a review, not a paper, a review on recent results on lithium-ion conductors from 1976. And then this is a paper from, I think, 2011. One new material was found, and it was a Nature paper. So these are like 35 years apart. By now it's over 40 years, and we're still working on this problem. So why is this so hard? Well, solid electrolyte materials that work in batteries have to satisfy a bunch of criteria at the same time. And this plot here from ARPA-E, I think, really illustrates that well. So there's these sort of conductivity and stability. These are all kind of atom level properties that you need to have. They need to be very, very much optimized. And then you kind of get over here, and now you're looking at things like processing ease, where you're thinking about like manufacturing scale. So there's a lot of requirements that you have to meet at once. And if we're searching for promising materials based on trial and error, just mathematically you can see that if you draw material at random, what are the odds that you're going to satisfy 10 criteria at once, which are probably hard to satisfy just one of them. But if you're trying to satisfy 10 at once, it's just going to be a lot harder to do mathematically. You're just going to have to do a lot more trial and error. So if you don't believe me, because I'm a PhD student, you can believe my advisor who said this to me in a meeting a few weeks ago. Predicting ionic conductivity is really hard. So if you were to look at a material and say, is this a good ion conductor? That's a very tough problem. You can't really answer that question without just making the material and measuring it, or doing these really time-intensive simulations. So predicting ionic conductivity is really hard. Is I think probably the short version to say all of what I just said. And so that's motivating us to think about this in a different way. So if we kind of back up and look at how things have gone, philosophically from the 70s to present, we have this timeline where we take a structure, the material structure, we call it X1. We go into the lab and we measure the property that we want, call it Y1. Maybe it's ionic conductivity. If it's good, it's good. If it's bad, it's bad. It's usually not great. So we go take another one, X2, and then we measure Y2. And we continue this, basically n times to present, hoping that we're going to find the right one. And we haven't really found the best one, but we have generated a ton of data and a ton of wisdom here, a ton of XY pairs. And so what we want to do is reformulate this as, let's not just keep trying things, but let's take this data that's already out there and let's reformulate this as a problem of supervised learning, where we are taking the x's we know and the y's we know and looking for this function f, which can map between the two of them. And in the material science world, this is a structure-property relationship. So the question driving us is, can we learn effectively from the data that we've already generated without having to generate a whole bunch more? And machine learning is really the way for us to do that, to hopefully go beyond trial and error. And just to give you a sense of the timescales involved here as further motivation, if we say, I think this is a liberal estimate, if we say it's 3 days to assess let's say, conductivity in a candidate material, probably more like 2 weeks or 3 weeks, but let's just say it's 3 days. There's 12,000 known lithium-containing compounds out there, so that's a 100-year PhD right there just to get through all of those. I'm not up for that, so I'm looking for other methods. But then, when we think about the fact that material space is really infinite because there's all kinds of different combinations of elements, or close to infinite, then this becomes just totally intractable. There's millions and billions of candidate materials that you could think of out there. So we don't want to just compute 12,000 things. We want to sort of reformulate the methods that we use to attack this problem. And that's where the power of machine learning comes in. So in our landscape here of accuracy of a scientific approach versus the size of the searchable space, so let's say like the number of materials you can assess in a given period of time, I kind of put this on the scale of like a grad student's attention span. Experiments are very accurate. They capture all the information out there, but maybe you can get through 10 materials and you kind of start to go crazy. Density functional theory simulations are a little bit less accurate, but you can automate this, go through hundreds to thousands. Machine learning is going to be less accurate still, but orders of magnitude faster. So you can get through billions of candidate materials. So if we want to accelerate the development of solid-state batteries, we have to beat trial and error, and we need a smarter and a data-driven path forward. So we started this problem by looking at ionic conductivity up here on the top, because that's been seen as, in the material science world, it's seen as a very tough problem, like Ichwei said, and it's a very time-consuming problem. So that's where we started our work. So I'm going to talk through basically 3 bodies of work that have come out of this. We'll start with building models for conductivity and screening all known lithium-containing solids. The second part is validation of the model and quantifying sort of how useful it is. And then the third part, we'll start thinking about how we can use this data to guide our work going forward. So just one more point on this sort of data-driven approach. So data analysis is really central to any kind of scientific endeavor. And in a conventional scientific method, data analysis usually comes at the end. So we propose a hypothesis on why something is happening. We go out and we identify the important data that we need to validate that hypothesis. We analyze it, and then we repeat the cycle. But what we're doing is we're really turning this thing on its head. So we start with gathering a bunch of data, and then we identify the important data, and we let the hypotheses sort of fall out of the data that we have. So we're not really going into it saying that we know what causes conductivity. We're hoping that the data sort of tells us what that is. So how do we start? So we went through the literature manually, looking through papers. There are no databases for these, or at least there weren't at the time. I still don't think there are, for these materials and their properties. So we're able to pull out experimental measurements of ionic conductivity at room temperature for 40 different materials. Excuse me. And these are all crystalline materials. These have well-defined structures that have been characterized. And so for all 40 of them, we came up with 20 features, which are essentially pieces of information that we think might have some bearing on predicting ionic conductivity. And some of them came from the literature, from things that people had proposed. Some of them just kind of came from our intuition on, we think this kind of makes sense, so let's look at that. And the first thing that we did was we just computed all 20 of these for the 40 materials, and we looked at them one by one just to see, does this one predict conductivity? Does this one predict conductivity? And the correlation coefficients are in this column, and you can see they're all pretty small. They're all less than plus or minus 0.3. So of our initial 20 guesses, none of them really were good predictors. So here we have to use a sort of axiom in machine learning, which is that if you have a bunch of weak learners or weak descriptors, you can put them together in a creative way and you can create a strong learner or a better predictor. So even though there's no single feature strong correlation across this diverse set, we hope that we can sort of creatively put these together in a way that gives us that predictive power. So to move forward, we have to choose a model that we want to use. We used a binary classifier. So this is just predicting essentially a yes or a no. So we broke the training set down into good conductors and bad conductors. We used a cutoff of 10 to the minus 4, so that's kind of like the lowest you can have and still have it be considered a good electrolyte material. That splits this up into about a quarter good conductors, about 3/4 bad conductors. And this is where the sort of Wild West aspect comes in, is because there's really no clear way forward. There's no conventions in this sort of space, especially machine learning with this small of a data set. And so it really, you really kind of have to improvise as you go. But we pursued this approach. We pursued a few others, and this was the one that we found worked the best. So we assumed this logistic form for logistic regression. And it has, down here in the denominator, you have this theta transpose x. This is a combination of features. Those are the x's. And the thetas are the regression coefficients. And so the question is, which of those 20 features, which combination of those 20, will give us the best predictive model for that data that we're training it on? And so the flow chart kind of looks like this. We take the 20 candidate hypotheses and the 40 data points, and then we want to find the best feature set. We want to fit it to the data, and then that gives us this model, which says essentially, with the data you've given me, this is the best way to explain ionic conductivity. Now, one of the good things about having a small data set, usually it's bad because you have problems with overfitting and it's just kind of harder to deal with. So we have to be very careful about that. But one of the benefits is that with a small data set, you can search the entire model space in a reasonable amount of time. And so we had, with this approach, we had 1 million candidate models, or over 1 million, about 1.5 million. And that corresponds to essentially every combination of 20 features we could think of. And we were able to actually just test all of them and find the best one. So for each candidate model, we fit it to the data, and then we measured the leave one out cross-validation error of that model, which tells you something about how the model is going to how well it will predict on unseen data. And that's what this solid red line is here. And we've plotted it against the number of features. So we find that there is a minimum in the cross-validation error here at 5 features. That means that there is basically one model of these 1.5 million, which gives us this error, and it's kind of the best model that we could find with this data set. I know there's a lot of lines in this plot, but I just would draw your attention to this dotted red line. And this was a control where we replaced all that feature data with 20 columns of random noise that was just generated by a random number generator. And we redid this fitting process. And so you can see that basically there's the error is about 3 times lower when we're using our real features than when we're using noise. And so that is just a confidence builder that we're building this model on real information, and we're really capturing something statistically significant here. And our hope is that this optimal model will give us an accurate guess about 90% of the time. So this is what that model looks like, and this was published about a year ago in our paper in Energy and Environmental Science. It has these 5 features here, which are all sort of easily interpreted in a material science context. They kind of make sense if you think about them in light of conduction. And there's some interesting physics here too. So I would point you to our paper to read a little bit more about that. Probably don't have the time to discuss it here, but there is some interesting stuff in there. But the main point is that this equation is based on 5 super easy to compute pieces of information. So whereas it would have taken us 1 week to get an estimate of conductivity with density functional theory simulations, which use physics, and you have to solve the Schrodinger equation and all this stuff, you have to move atoms around. This takes us, if we set it up in an automated script, less than a second, like a microsecond to compute this. So this is a huge improvement in speed. So I just wanted to take a quick philosophical aside at this point to share you this quote. I love this quote from Bertrand Russell, and I think it sort of sums up how we think about this sort of work. So it says, "Science does not aim at establishing immutable truths and eternal dogmas. Its aim is to approach the truth by successive approximations without claiming that at any stage final and complete accuracy has been achieved." So this equation here is, certainly not the ground truth, the universal law of conductivity, but it is sort of the first attempt, the first iteration of building a model like that can be deployed across any arbitrary set of materials. I think another way of saying this, less eloquently but more concisely, is to say it's the best we can do with the data that we have. So now that we have this model, which is about 1 million times faster than the incumbent methods, that is so much faster, it will allow us to screen every known candidate material out there. And we found over 12,000 of them in the online database of the Materials Project, which is curated at Lawrence Berkeley National Lab. And we started screening through them. And we also included 6 extra screening metrics, which were, these weren't built from machine learning. These were built on kind of simple heuristics and information where we could get it. And these are, here's this piece of information. These are all kind of different parts of that graph from ARPA-E that I showed at the beginning. So conductivity isn't all that matters. Here are 6 other things that we can use to help our screening. So when we take these 12,000 candidate materials, we first applied these 6. Don't think about conductivity yet, just apply these 6. And that actually gets it down significantly to a little bit over 300 materials. Still too many for us to do 300 experiments or 300 simulations. So this is where we take our conductivity predictor, apply it to those 300, and we're able to get it down to 21. And lo and behold, we're able to do the first multi-property screening of all known lithium-containing compounds for solid electrolyte materials, because we have this conductivity model, which is so much faster than what we had before. So the approach that we took was we took these 21 most promising materials and we what we call publish and pray. So we put them out there in the literature. We didn't really know much about these materials. We didn't really do much validation before we published, but we think it's important to approach these sorts of studies that way. You don't want to sort of conflate validation and model building, because then you can kind of get into dangerous territory where your model is contrived around your validation points. So we put these out there. We didn't really know much, and that takes us into the next part of the talk, which is validating this model and discussion of did we actually find anything interesting. So this is the long and short of it, is that of those 21, we found about half of them, we found 10 of them showed really exciting levels of lithium-ion conduction at room temperature. And we found this through doing these physics-based simulations. We're a computational group, so this is kind of our wheelhouse, although we have been working with some experimental groups as well to do that sort of testing. But the approach we take is to simulate density functional theory, molecular dynamics simulations, which is where you basically set a temperature and you just let the atoms rattle around, and we're watching for lithium motion. So this is a MSD, a mean squared displacement plot. This is a common way of showing this. Essentially, this is tracking how far lithium migrates in time in these different materials. So every different color is a different material, and this is how far lithium is moving in these simulation times. This is really short. We're talking on the order of picoseconds. These physics-based codes are really that slow that we have to operate on this time scale. But the slopes of these curves are what tell us about conductivity, which is our original metric. So if we, and I should mention, we also have to simulate these at high temperature because conductivity is just so slow at room temperature that we'll never see it. So we could simulate it for a year or two. And at room temperature, we might see some motion, we might not. So really the standard way of doing this is doing it at higher temperatures and then extrapolating down to room temperature. So of these materials that we have, we can kind of break them down into 3 categories. So we have 4 materials here which we find are really on par with the best known materials out there. They're about 10 to the minus 2 Siemens per centimeter. which is really exciting. Then we have this kind of, still exciting, it's 10 to the minus 4. This is near what we said our cutoff of good materials was, but not quite as exciting, but still good predictions. And then we get several materials that don't really show any motion at all. And so taken together, this gives us this 50% hit rate for the model, or success rate. So now that we know that, the next question is, how do we judge a 50% accurate model? Most of us don't want to be accurate in 50% of the things that we do, but the way to judge this is really to compare it to the incumbent methods. How much improvement is this model offering us over what we would expect to do if we didn't have this model? And a lot of times that really comes down to, as John said, comes down to random guessing. So is 50% better than random guessing? And if so, how much better? And that's a very quantitative question, which is really difficult to answer without actually doing trial and error. There's not really a way to know what trial and error is going to give you until you do it. So we reluctantly had to just do a bunch of trial and error in order to get some statistics here. So we have this list of materials that the machine learning told us to simulate. We started simulating them. There's some subtleties of how we count successes here. So we'll say the success rate is between 35 to 50%. There has to do with things with melting, et cetera. Not super important. But then we started doing the exact same procedure, but we were just simulating materials that were chosen at random. And what we found in that case was that the success rate was about 10%. So you can see right away that there's going from random to this machine learning driven effort, you have about a 3 to 5 times, depending on how you count this, improvement in the rate of successes of our effort. And this histogram shows it demonstrates that we have 3 categories of bad conductors, medium conductors, good conductors. The gray bars are what we find with random searches, and then the red bars are what we find with machine learning guided searches. So you can see you get about half the duds that we had in the random search, and we get probably 4 times more really great conductors when doing this. So I think there's definitely a tangible, undeniable improvement that's offered here by machine learning. And I think it's really important just to emphasize that this 3x improvement in guesswork came from a model that was trained on 40 data points. And if you were to ask someone, say from Google or from Facebook, what 40 data points means, they would probably tell you it's 0.0, statistically speaking. From their perspective, this is basically no data at all. So I think it's just worth pointing out that even small amounts of data, if you sort of work with it the right way, can give you really tangible improvements in the way that you discover materials and that you search through space. So we're pretty excited about that. But the next question for the critical scientists in the audience is looking at this as saying, well, scientists are hopefully better than random. They're not totally randomly guessing. So how does this compare not to a random guess, but to a scientist that's maybe trained in this field? So this is sort of the Garry Kasparov versus Deep Blue analogy for material science. So this is what we did. So we took a list of 25 materials, and we gave it to a group of PhD students here in the material science department that are trained in electrochemistry, essentially. And then we gave that same list of materials to the code, to the machine learning algorithm. And we said, find us the good lithium-ion conductors in this batch of materials. And so we have 2 axes here. So this is basically accuracy of the predictions, and this is speed. So here on the left, this is the random guessing baseline. So there's about 10% of those materials are good conductors. That's what we would expect to see if you were guessing at random. And the PhD students double random guessing, basically. They have an accuracy that's twice as high, which is great. This actually surprised me because I thought that most of us were guessing at random. I think I'm usually guessing at random, so I think it means most PhD students are smarter than I am. I don't know, but they're definitely beating random guessing by a factor of 2. But then the logistic regression model trained on 40 examples beats random guessing by a factor of about 5 and beats the students by about 2 to 3 times. And if that's not good enough, we have, this is a log scale here, it takes about 1 million times, or it's 1 million times faster for the machine learning model to make those predictions. So students would take about a minute, and the computer takes, as I said, less than a second. And for reference here, we have these physics-based models which are used to validate the predictions. We assume these are 100% accurate, so that's why they're up here way on the right. but they're incredibly slow. So each material takes several weeks to get a good validation for. So this is sort of our Bermuda Triangle of machine learning and students guessing materials. So what we've learned from this is that there's a few I think ways to think about the value that machine learning brings to these sorts of problems. So machine learning offers several times guessing that's several times more accurate than trial and error, and potentially also than human guessing. It's less likely, in general, it's likely less accurate in general than physics-based models, but it's many times faster than both of these approaches. So we often have people that come to us and ask, sort of when is it appropriate to apply machine learning to a materials problem? And I think this is kind of the answer. If you're working in a domain where it takes you a very long time to get a data point, so you really need improvements in speed, and you really just want to be able to beat, to be several times more accurate than trial and error. So if you're doing trial and error, then that's great. That's sort of the niche I think that machine learning enhanced material science is well suited to fill. And so finally, in the remaining time, which we're doing okay? Okay. The third part of this is using this data to think about sort of where we go from here. So we found some really interesting materials. We have a couple of patents on them, and we're really excited about those. But there's also we generated a lot of data that we can use to think about where does the community go? Where should the community be? How should we sort of reorient ourselves in light of what we found in this study? And so two questions kind of come to my mind after doing this work. One of them is, where do we look to find these? We're looking for the promising outliers, the good ion conductors. Where do we look to find those promising outliers? And can we quantify the likelihood of finding them? And so this is a question that's really difficult to answer most times. Like, what is the likelihood that I'm going to make a major discovery? That's a difficult thing to answer, especially with first principles methods. And it'd be great if we could say something about how likely am I to make a discovery based on if I'm looking here versus if I'm looking there. So I kind of mentioned stability in the first part of the talk, but I'd like to come back to it here. So electrochemical stability is also a very important metric in these materials. We've talked about conductivity so far. So conductivity is kind of indicative of power density. It has to do with how much current you can get out of the cell. The electrochemical stability window tells you about the voltage you can have across the cell. So that's more like energy density. And here are a few of the well-known solid electrolyte materials that have been reported in the literature on this, in this landscape. And you'll notice that we really need to be sort of above 10 to the minus 2, kind of right up in here, and there's not a whole lot up there. So optimizing both of these at the same time is a really difficult challenge. Getting good ion conductors is hard enough, but getting good ion conductors that are electrochemically stable over a wide range of voltages is even harder. So here's coming back to our schematic of the battery. So here's our electrolyte. And we're basically asking 3 demands of it if we move beyond conductivity. So we know that we need a good ion conductor, but we also need it to be stable against oxidation at the cathode. So here it's touching the cathode, and at this interface, it tends to be oxidized. And if it becomes oxidized, then usually, through one way or another, it tends to break down. So we'd like to avoid oxidation there. And at the anode, it's touching this really low voltage surface, and it will tend to be reduced. So can we find, basically we're looking for a material that can satisfy all of these at once. As I said, that's a very tough optimization to do. One thing that has been proposed as a way of making this a little bit easier is to split the electrolyte up into 2 electrolytes. Now, both of them need to have good ion conductivity, but electrolyte 1 is touching the anode and not the cathode, so it only needs to be stable against reduction. Electrolyte 2 is only touching the cathode and not the anode, so it only needs to be stable against oxidation. So you can kind of ease the demands on these materials a little bit more by doing that. But of course, you introduce additional difficulties. Manufacturing these things is really hard to get 2 materials to stack right on top of each other with minimal defects and interfacial resistance and all that kind of stuff. So it's not really clear. This has been something that's more recently thought about, and it's not really clear, I think, which strategy is better. So these are the sorts of things that we're thinking about. So if we want to do this optimization of conductivity and stability, this is our map, and we like to say, where do the materials lie in the space? And one trend that is sort of known out there now is that, let's say you can write any material like this. It has lithium in it. It has a bunch of other junk, and then there's an anion in there somewhere, like oxygen or fluorine. And it's known that anion actually is pretty predictive of where these materials will lie in this space. So fluorides and oxides tend to be poorly conductive, but pretty stable. Whereas sulfides tend to be very good conductors, but also not very stable. And these trends have sort of emerged in recent years just through a few different data points for each family. Everything else hasn't been looked at as extensively as these three families, but is thought to kind of lie in here somewhere. But we want the outliers, as I said, that are up here on the upper right. And you can see it's a difficult question to say, if most of my data is here, or most of my data is here, is it easier for me to get from here to here, or from here to here? It's not a trivial question to answer. And I've heard these questions asked a lot of times in conferences, et cetera, where people say, am I more likely to find an outlier that's an oxide or an outlier that's a sulfide? And no one really knows. But it has really big implications. If you're setting up a research program, or you're a program manager at the DOE, even if you have a little bit of information on which one of these is more likely to succeed, that's a really valuable piece of information. So using the models that we developed in the first two parts of the talk, we can now quantify this trend and provide a little bit of insight there. And as I said, this is very difficult to do with first principles. So if all that you have in your toolkit is the Schrodinger equation, it's I don't even know really where you would start. It would be a very difficult problem. But because we have these models which allow us to generate a lot of predictions very quickly, we can now answer this question with data. So we take our landscape here. We can just compute conductivity now, or make a prediction of conductivity. And we can use some DFT stability methods to compute stability for 12,000 materials. And we can throw it up on this plot and kind of look at where the data lies and see if it's telling us anything. Again, this is sort of the best we can do with the data that we have. And hopefully we'll find the yellow brick road, which is leading us to the solid state, the elusive solid state battery. So that's what we did. So we took our conductivity model and we took existing electrochemical stability analysis methods, which have been developed largely by the Sater group at UC Berkeley. And we computed, this is conductivity on the x-axis, and this is oxidation potential here. This is reduction potential here. And we plotted it for over 1,000 materials and broke it up by that anion in the structure. So all these red dots, these are the oxides. These gray ones are fluorides. The black ones here are sulfides. So you can see it kind of follows that trend that the community has sort of deduced from the limited data that we have. And that trend is also more or less kind of true with reduction as well as with oxidation. To clear things up a little bit, we just replaced the data by essentially the covariance. These ellipses designate one standard deviation of the data in all directions. And then you can see starting to look a little bit more like that plot that we saw. So once we have this, we are well on our way to quantifying how likely it is that we can get up here. Because we can see these as probability distributions, and we can say, okay, the data that's been generated has come from underlying probability distributions that look a lot like this. And if we're going to keep sampling materials and reporting them in the literature, it's probably going to come from that same distribution. Essentially, what we've done in the past is probably indicative of what we're going to do in the future. And we can quantify the likelihood that we get up there by using statistical methods such as building Gaussian distributions and finding cumulative distribution functions of this regime of outlier space. And so that's what we're doing. So we're fitting Gaussians to each of these families, and we're saying the data for each family likely came from this probability distribution. And if it did, how much of the tail of that distribution is in my promising outlier region? Because there are no data points there, so it's we can't really count them, but we can say what does the tail look like up there? And we're essentially using the past to try to predict the future. And we generated a whole bunch of numbers, which I should not be shown on a slide because there's way too much text. So I just wanted to put the central conclusions here that we found. If we want a fast conducting stable material, we're able to quantify that the oxides are sort of in an absolute scale are pretty unlikely to yield these promising new materials. And that's an interesting insight because a lot of research on this so far has been focusing on searching the oxides. They're very easy to make because you can make them in air. There's a ton more data on oxides than anything else. But we found that oxides, really on the scale of these materials are pretty low. The sulfides, turns out, are also unlikely, but are more likely than the oxides, about 10 times more likely. But that something else that we showed in the graph is really where things get interesting. So the things that are in between the sulfides and the oxides start to look really promising. And the things that are in between are the halides, the chlorides, the bromides, the iodides. And these are materials where they haven't really been extensively searched. There's not a ton of data there. But the data that is there is pointing us towards something really interesting. And of course, what we know also is that certain families are better against reduction, certain families are better against oxidation. And so that has some implications for sort of this final question that we want to answer, which is, how likely am I to find the wonder material which satisfies all my criteria at the same time, which gives me a lithium metal anode, which gives me a high voltage cathode, and gives me fast lithium ion conduction. So coming back to this 1 versus 2 electrolyte system, if I want to do this, if I want to build this lithium metal high voltage, wonder material battery, I can do it with 1 electrolyte or I can do it with 2. If I do it with 1, the probability of success here is the probability that, at least from the materials discovery perspective, that I can find 1 material that satisfies all the requirements. But if I do it with 2, my probability of success is the probability that I find 1 good conductor that is stable against oxidation times the probability that I find a good ion conductor that's stable against reduction. And we now have quantitative numbers to do this calculation. So for the 2 electrolyte case, we find that the likelihood of getting the first criteria is about 90%. There's a lot of good materials for that that are fluoride based. And the likelihood of the second one is 10%. So the joint probability here is 9%. So that seems pretty good. And the reduction stable material is a nitride. So it's basically this 9% corresponds to a fluoride and a nitride-based dual electrolyte. But if we want 1 electrolyte, we don't get to mix a fluoride with a nitride. We have to choose 1 material. We have to find 1 material from 1 family that is likely to meet all these criteria. And the chlorides are the most likely, we find, the most likely material family to do that, but they are incredibly unlikely. They are about 0.06%, and that's the most likely of all of the options that we have. And so we can see that in going from a 1 to 2 electrolyte system, we're 150 times more likely to discover good materials for this purpose. So there are certainly more. There's more to this puzzle than just the materials. Like I said, we have to think about processing. We have to think about all sorts of stuff. But the first step is you have to find good materials for it. And this is a quantitative roadmap that says you're 150 times more likely to find success if you start searching for this architecture than if you do this one. And just to demonstrate that a little bit further, these are the likelihoods for the various families. These are phosphides, nitrides, chlorides, and everything else is basically down here. The likelihood that you can discover a promising outlier that is stable against lithium metal, a good ion conductor, and is stable above a cathode potential of X. So pretty much everything goes to 0 at about 2 volts. So it's very unlikely, we find, that you can find a material that will allow a more than 2 volt lithium metal battery, and that kind of defeats the whole purpose. The chlorides are the only ones that extend into this regime of 4 to 5, which is where we need to be. Although the odds, as you can see, are essentially 0. It's very small. So again, so how do we interpret these 150x insights on 1 versus 2 electrolyte batteries? Well, these insights are generated from models that are trained on data that is an incomplete data set. And you could say, well, everything you've just told me is, comes from this model that maybe works half the time. So why should I believe this? But again, it comes down to the way that we think about this as being the best we can do with the data that we have. And the urgency of the energy challenge that we're faced with means we don't have a whole lot of time to continue in doing trial and error. And it becomes really important for us to sort of squeeze all predictive power out of the data that we can get. And in the worst case scenario, that the models are the models trained on this data don't have much predictive accuracy, all that happens is that we're reduced to going back to trial and error, which is essentially what we're doing, what we're doing anyway. So we see this as sort of being, this is the most informed way forward. Could be wrong, but we'll only get better with time. So with that, let me sum up on these pieces of work. So we deploy machine learning to enable the first holistic screening of all known lithium-containing compounds about 1 million times faster than state-of-the-art methods. That's about 3 times faster than random guessing. And sorry, 3 times better than random guessing and 1 million times faster than state-of-the-art. And that gives us several new materials for development, and also can give us some of these high-level insights on different strategies and how likely they are to succeed that are really difficult to get from physics-based approaches. And so this, again, coming back to this is really what excites us in thinking about how important 40 data points can be. And if we go forward into the future and really commit ourselves as a research community to cataloging this data really religiously, it's really exciting to think about what 500 data points would be able to get us, or what 1,000 data points would be able to get us if 40 can already get us this much. So we know for sure that the demand for clean energy is going to increase. We know for sure that computing power is going to increase. We know for sure that the amount of materials data is going to increase. And what we believe is that these small amounts of data can be really important. They can drive significant improvements. I think eventually batteries, full battery architectures will be able to be designed this way, from nothing or just from data, rather than really extensive trial and error searches in the lab. And this approach is also very general, so it doesn't have to be stuck to batteries. It can accelerate efforts in solar and catalysis. Jens Norskov has been doing some great work in this vein on catalysis here at Stanford. And electronics. There's a really exciting future in store for these approaches and applying them to the energy sphere. So with that, I will acknowledge my advisors, Evan Reed and Each Way, for their guidance here, as well as my lab mates in Evan's group. And would definitely like to acknowledge and thank the Tomcat Center for funding this work through one of the seed grants that we have from them. And to, of course, thank Precourt for hosting me today. And we'd be happy to open it up to questions.